Some of you whose names I know are already there. Okay, so let's start. Yeah, recording has started. Good. So let me go to the plan for today. Perhaps it makes sense to show you the last lecture. Okay, this was lecture number 12. That was on topological groups, continuous homomorphisms. We saw some equivalent formulations for hausdorffness for topological groups. We'll revise that. We also showed any discrete subgroup of Hausdorff group is closed. We looked at examples. Then we talked of homogeneous metric spaces, examples and non-examples. And then homogeneous topological spaces. And I asked you whether the closed interval 0, 1 is homogeneous. You are supposed to prove rigorously it's not. And whether the underlying topological space of a topological group is homogeneous. Yes, by translations. We talked of separatedness properties T1 and T2. T2 is Hausdorff, T1 means every point is closed. And we showed it's the same for a topological group. Then we looked at discrete subgroups of R. The exercise was show that they are cyclic. Have you guys succeeded in doing these exercises? Okay, your tutors will soon find out. This exercise somebody answered on the spot by saying send m comma n goes to m plus n root 2. That was the correct answer. Then we asked that if there is a topological group and H is a subgroup which is discrete in the induced topology, then H is necessarily closed. And we proved it using this argument, using a small neighborhood. But first of all, I asked for an example of a topological space and a subset which is discrete but not closed. And I think Roshani gave the example right away. Like here's the example. But this doesn't happen if your subset is a subgroup of a topological group. And we proved it here. And then I said, see you on Monday, 20 December at 3:30. So that's what we are doing now. So this was the last lecture review. And now I'm coming to today's lecture. Okay. So I want you to recall the concept of the automorphisms of an object in a given category. So as example, here we are. Suppose our category is that of metric spaces and distance preserving maps. Then such an automorphism will be a distance preserving bijection. I'm going to ask you a question. Suppose my X is the real line with usual metric. R usual. Then tell me some automorphisms that preserve the metric. So I can hear that one of you is saying send X to X plus C. Oh, another answer I hear is send X to lambda times X. But is that okay? What should lambda be? Yeah, you're right. Lambda has to be plus minus 1. And so I can in general combine these together and I'll have X goes to X plus C. This is one kind of thing, and X goes to minus X plus C. That's the other kind of thing. These are all the possible automorphisms which preserve metric. Nothing else. So you have to prove it. There is nothing else. Yeah. So that's automorphisms in the category of metric spaces. Now all the automorphisms form a group because composite of two automorphisms is again an automorphism. So let's look at some examples. This happens in any category. So in any category, the automorphisms form a group. Automorphisms are possible in any category. So let's look at different categories. I look at the category of sets and my object is the finite set 1, 2 up to n. Then what are the automorphisms of X? So in the category of sets, what are isomorphisms? Yes, you're right, bijections. So automorphisms of X are the same as bijections of X with itself. So what are they in this case? Yeah, somebody answering? Yes, you are right. So that is the permutation group Sn. Because given any, you take this, and now you simply want to send something to something, something to something, something else to something in a bijective manner. That means these are all called Sn. So you are very familiar with this automorphism group Sn. Okay, let's look at another example. That example we saw above. X is the real line with metric x minus y. And so what is the automorphism? And my claim is every such automorphism can be written as a matrix lambda C1. Okay. This X goes to lambda X plus C, where lambda is plus minus 1. So this can be represented as this matrix. And how to act on X? You represent any X by this. And the answer is, what is it? Lambda X plus C and 1. So this entry which is not written is 0, 1. So when you represent any point as the matrix x comma 1, its image is lambda x plus c 1. So which means x is going to lambda x plus c. And you can see the composite behaves correctly. So if I take another transformation, x goes to, let's say, mx plus some other translation t, where m of course has to be plus minus 1. Now let's compose these. So x goes to lambda x plus c, and that in turn goes to m times lambda x plus c plus t, and that is equal to m lambda x plus mc plus t. So this is also transformation of the same kind, because m is plus minus 1 and lambda is plus minus 1. This m lambda again will automatically be equal to, something strange happened. Okay. This is again equal to plus minus 1. And so I need to make some space here. And so what has happened is this entire transformation can be represented by the matrix m lambda mc plus t 0, 1. This is the composite transformation by the way we represent any matrix. And then you can see this is just the matrix product m t 0, 1 times lambda c 0, 1. Is that okay? So all matrices of this type, okay, form this group. And so this group is abstractly plus minus 1 times R. because this lambda is here and here, but group structure is semi-direct product. Have you heard the name semi-direct product? Yeah. Has anybody heard of semi-direct
Yes,
products? Yes. So this is a semi-direct product. Okay. So in your algebra course, perhaps you'll learn about semi-direct products by action. So this automorphism group of the metric space real line is the semi-direct product of this with this. Translations are going to form a normal subgroup, and plus minus 1 is the quotient group acting on translations by minus 1. Okay. Here's my next example, which I had given as an exercise. I take the category of rings, and now my ring is R with the usual addition and multiplication. So what are self isomorphisms R to R? Okay. Ring isomorphism.
Identity, right?
Correct. The only possible one is identity R, and you were asked to prove it as an exercise. Have you guys done this exercise? And so
Yes.
what? So this is the trivial group. So this we know is the matrix group. Okay, how about this example? Let's work in the category of groups. So my object itself is a group. And my group is S3, the permutations of 1, 2, 3. So what is the automorphism group of S3? Yeah, you know any automorphisms of S3? Any bijection of S3 with itself? Yeah? Can you give me some straight away?
It's S3, right?
Yeah. So what are the automorphisms of S3? This is the topology class, right? So you should be able to answer such questions fatafat.
So take an element and say 1, 2, and then like translation types.
No, that's not automorphism of the group. Automorphism of the group has to be a group isomorphism. Well, how will S3 act as automorphism on S3?
So G goes to.
You heard inner automorphisms. Have you heard the word conjugation?
yes, sir.
So I asked you. So prove your answer. Okay, but don't take up the time of topology tutorial with the solution of such questions. Yeah, but it's important you are able to solve these things to do topology. Okay. So now you understood what automorphism. Now let's get back to hausdorffness. Okay. So I am claiming that the following are equivalent. X is any topological space, and I am saying the following are equivalent. One is X is Hausdorff. Second is that the diagonal is closed in X cross X. And we know that these two are equivalent anyway. This we proved in great detail that X is Hausdorff family if diagonal is closed, and I labeled it as the most important single statement of the month. Okay. The third equivalent statement I have given you, and this I gave you long ago as well, is that if I any graph, so this is X, sorry, if I any map, and this function f is going to have a graph which I'll show by this violet color. This is the graph of f. Graph of f is the set of all chota y and f chota y. So that y belongs to y. This is the definition of graph, one of the first things you learn in higher secondary or college, I don't know when. So this graph is therefore a subset of y cross x. Okay. So this should be closed. If x is Hausdorff, then this graph is closed. Conversely, if For every such map, this is closed, then X is Hausdorff. Okay. Tell me at least in one direction. You see, you shouldn't work too hard with points and whatnot. All these examples are to be done by simply drawing arrows and using universal properties. So here, take y to be equal to x and f to be equal to identity x. Then what is the graph? Graph is the diagonal. Correct. Thank you for saying graph is the diagonal. I was afraid again somebody will launch into saying, oh, graph is the set of all ordered pairs, small x, blah, blah, blah. Diagonal, one word does the job. Now you are introduced to diagonal. You don't have to every time say small x, blah, blah, blah. Okay. So so this amounts to the diagonal being closed in the special case of y being equal to x and f being equal to identity. But I am also asking you to prove it the other way around, that if x is Hausdorff, then for every such f, the graph is closed. And here I want you to simply notice the following. I get a map from y cross x to x cross x. And this maps is the map f cross identity x. Yeah. In other words, it sends y comma x to fy comma x. Okay. This map f cross identity is a continuous map. This was the argument we made just universally. And we said this is okay even in groups. If y and x are groups and these are group homomorphisms, then again this would be a group homomorphism, etc., etc. I hope you remember it. Now I'm asking you, let's call this map G. Okay. Then what is G inverse of diagonal of x? That is just the graph of f. Graph is the inverse image of diagonal. So if x is Hausdorff, then the diagonal is closed. Therefore, its inverse image, which is the graph, is closed, because under a continuous map, inverse image of closed is closed. So we have proved this equivalent to the original. Without taking a single neighborhood, without taking a single point, nothing. Just one equation gives the proof. Okay. Next equivalence statement. For any space Y and continuous maps Fg from Y to X, the set of all Y in Y, so that Fy is Gy should be closed in Y. Y is 4 equivalent to the others. Again, very simple argument. Take so I have X, I have X, I have X cross X, and I have the two projections P1, P2. On the other hand, I have Y and I have the two maps F and G. Therefore, by the universal property of product, there exists a unique map, and that map you will write as F comma G. Making this and this commute. That's okay. And now under this map, let's call this map H. There exists. So what is H inverse of diagonal of X? And that is the equalizer of F and G. This equalizer of F and G is all those points where F and G take equal values. That's the inverse image of diagonal. If this is closed, then the equalizer is closed, because the inverse image of diagonal under a continuous map. So all the time we are proving important maps to be continuous, sorry, important sets to be closed without doing epsilon delta. We proved this is closed, no epsilon delta. We proved this is closed, no epsilon delta. We proved this is closed, Hausdorff, no epsilon delta. So you see the advantage. In all your early years in college, you had to all the time cleverly struggle with epsilons and deltas and take epsilon by 2 to begin with, or take epsilon square, or do this, do that, and then somehow now show it is less than delta and therefore something continuous. And now find something tending to take a convergent sequence, and now the points are inside, therefore the limit is inside, again make some argument with the sequence. All of it is completely avoided. And the arguments are very categorical, so the arguments are quite transportable to other categories in appropriate situations. Okay. Now let's suppose that we had a topological group. So far we had a topological space, and now we have topological group. Then I am saying Hausdorffness is equivalent to following 4 extra statements. All these statements, of course, are equivalent to Hausdorffness because we are only talking of Hausdorffness of the topological space of a topological group. But if it's a topological group, using the group structure, the Hausdorffness is equivalent to all these things. So we showed G is Hausdorff. Okay, if G is Hausdorff, then obviously every point is closed. So let's look at the proof. This implies okay, for in any Hausdorff space, each point is closed. So obviously 1 implies 2. Now 2 implies 3. Well, every point of G is closed and G is non-empty. So there is some G, and therefore there exists a point G that is closed in G. Every doesn't mean there exists unless you also know something is non-empty. It's the same example back to every time I went to the top of Mount Everest, I had Bhel Puri there. But there is no single instance of time when I was on Everest and I had Bhel Puri, because I simply never was on Everest. So this doesn't imply this in that particular situation because the set was empty. So G is non-empty, so this implies this. Now what this implies this? Because G is a homogeneous topological space, translation by G takes E to G. Which translation? Right, left, whichever. But we, for the sake of definite, let us say right. We could have said left. And so a self-homeomorphism carries the point G to the point E, and under any homeomorphism, closed sets go to closed sets. So if G is closed, then E is closed, or if E is closed, G is closed. So this implies this. Now I am going to say that I am going to show that this implies this again. If the identity is closed, then G is Hausdorff. How do I know? Because I consider the map G cross G to G, sending G comma H to G H inverse. This is continuous. And inverse image, let's call this map F. And F inverse of E is the diagonal of G, because G times H inverse is E, which means G equal to H. So inverse image is diagonal. And therefore, if E is closed, then the diagonal is closed. And which means G is Hausdorff, because the basic most important statement we have seen is X Hausdorff, and the diagonal is closed. Now let's go from here to here. If the identity is closed, then every discrete topological subgroup H of G is closed in G, or actually we have proved it last time. We have proved that if G is Hausdorff, then that implies writing this double arrow of such length is not easy. If G is Hausdorff, then every discrete topological subgroup H of G is closed in G. That's what we proved last time. That was the last theorem in last lecture, which we reviewed this morning. Okay. Now, from here to here, that this number 6 says there exists some topological subgroup that is closed in G. So if every discrete topological subgroup is closed in G, how do you know there exists some topological group that is closed in G? That's because G if G, okay, let's not, I will, so so that proof is simply by saying E inside G is a discrete topological group. So, because on any single point, the induced topology is a discrete topology. So if every discrete topology subgroup of H is closed, and here is a discrete topological group, which means E is closed. And E is closed, that is this statement. There exists some topological subgroup H that is closed. So suppose H is a closed subgroup. Sorry. Closed and discrete. Because H is discrete, E is closed in H. So E is closed in H because H is a discrete topological subgroup. Wait, here I have made, that is too bad. I have said there exists a topological. Let me put the missing word here. Okay. All right. Okay, there we are. So suppose there exists some discrete topological subgroup H that is closed in G. I take that discrete closed subgroup and take its identity that is closed in H. You are already told that H is closed in G, therefore identity is closed in G. That is this statement. And this statement, you already know how to come back to this statement. So you have this whole wave of statements interlinked by very nice natural arguments. So we have looked at hausdorffness of topological groups in multiple ways, hausdorffness of topological space, first of all, in multiple ways. So at this point, I'm going to stop on the subject of hausdorffness and begin on the notion of connected topological spaces. Connectedness is a very important notion in topological spaces. So today we will discuss connectedness in the remaining part of this lecture. Perhaps it will spill over to next, or who knows, we'll revisit it later also. And besides connectedness, there's another notion that I want to address, very, very important, which we have not touched, that is compactness. So a bit of connectedness and a whole lot of compactness is my plan for the remaining weeks. But of course, my plans are not hard and fast and they keep changing. However, what I want to do is all the time show you very interesting things which are relatively elementary and are connected to rest of mathematics. Okay. So before we begin on connectedness, any questions on hausdorffness? 10, 9, 8, 7, 6, 5, 4, 3, 2. No, nobody is doing that. And so time is up and there are no questions. Okay. All right, so let's begin with connectedness, and I want to begin by telling you the definition of connectedness. Wow, I should make more room here. So here is the definition. Something has gone wrong. Okay. Definition. Space, a topological space X is called disconnected. This is the opposite of connected. If there exist open subsets U and V in X, so that U is not equal to empty, V is not equal to empty, U is not equal to all of X, V is not equal to all of X. So these are proper whatever open subsets such that U, okay. Why should I say all these things? So I don't have to say all this. U is non-empty, V is non-empty, but U intersection V is empty and U union V is all of X. If such open sets exist, then X is called disconnected. So I partitioned X into two sets. Partition meaning they are disjoint from each other and their union is everything. So I partitioned X into two open sets, both non-empty. Then I say X is disconnected. And definition, X is connected if X is not disconnected. So before I go on, let me ask you, have some of you at least seen this definition? देखा है क्या? Okay. People who have seen it are answering yes, but I want to hear an answer no. Then I'll spend more time on it. Somebody answer no? No, I have not seen it. Nobody is answering no. So you have all seen it. So it must be pretty boring. Okay. But I must do a mic checking. Are you guys still there and can you hear me?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
And all of you have seen the definition of connected. In that case, I should ask whether I have written it correctly. Have I written the definition correctly? Do you agree with this definition? I didn't go and look at any book, obviously, and I might have made a mistake. Bolo. Looks correct? Okay. So now let me ask you a question. Oh. Let me change it to questions. Question. Is the empty space X equal to phi or X equal to empty set? I also start calling it phi with you guys. Is the empty space phi connected or disconnected? Let's be democratic. Are there more votes for empty space connected or more votes for disconnected?
So
What do you
it's
think?
connected.
It's connected.
How do you vote?
By just saying your opinion.
Okay, connected for me then.
Well,
It's a
so
connected.
all voters are all connected. What kind of democracy is it? Everybody has the same opinion. Anyway, all right. Yes, so empty set is indeed connected because it's not disconnected. Disconnected requires the existence of two non-empty open subsets. It has no non-empty open subsets. It has no non-empty subset. So it is obviously cannot be disconnected. So it is connected. Okay. Now here is a basic property of continuous functions. So let me draw an arrow here. I have this x and I have y and I have continuous map and fx is equal to y, which means onto, projective. Okay. Then I'm saying that x is connected implies y is connected. This amounts to saying the contrapositive, which is y is disconnected. This must imply that x is disconnected. And suppose y has a disconnection u union v. This, let's call it a disconnection. There's no such word as far as I know in books, but let us temporarily call such a pair uv as a disconnection. Should we call it breaking up? I don't know, as a disconnection of x. So suppose this is a disconnection. So u is not empty, v is not empty, and u intersection v is empty. Then that will mean that f inverse u is non-empty. How do I know if f inverse u is non-empty? Because this is onto. So u has some point in it. So there's some point in x which maps to it. Therefore, this is non-empty. F inverse v is non-empty. And this is a disconnection. Disconnection of x. Because their intersection, you're going to have that f inverse of u intersection v. As you know, f inverse preserves intersections. F inverse u intersection f inverse v, that is equal to f inverse of empty set, and that is empty. Yeah, so and union is everything again. F inverse of y is equal to x always, regardless of whether f is surjective or not surjective. So if y has a disconnection, then x has a disconnection. Which means if x does not have disconnection, then y does not have disconnection. Which means if x is connected, it's y connected. So often people express this by saying that the continuous image of a connected set is connected. Now, all these definitions, etc., are no good unless there are interesting examples, which is why all the time I am trying to give you examples for every concept that we develop. And when connectedness, as far as connectedness is concerned, in the usual topology, by usual topology, I mean the kind of topology which is important in engineering, in physics, in differential geometry, and in analysis. In that kind of topology, as against there is a lot of application of topology in, say, number theory or algebraic geometry, where the spaces are very different. They are not made from real numbers. But the spaces that come up in science, engineering, and analysis are somehow made from real numbers, and which is why real numbers are called real, because the Euclidean space and various things in physics are related to real numbers. So for these real spaces, If we want to understand connectedness, it is important to understand whether the real line itself is connected, or the closed interval is connected, or the open interval is connected. You know, open interval is all of real line up to isomorphism. So that's not a different question. You can ask whether semi-open, semi-closed interval is connected, left open, right closed, or whatever. You can ask such questions. So this leads to the most basic theorem in analysis at the level of first year undergraduate, which says that the interval 0, 1 is connected. Now, is it okay that I leave this as an exercise to you and you solve it without looking at your books? I am sure a proof of this is given in your basic calculus book, which is taught in first year BSc. But
Yes, sir. Yeah, it's okay, sir.
Yes to what? It's given in your calculus book, or you will do it as an exercise?
Exercise.
Exercise. Good. In that case, I am going to leave it as an exercise. Now, there are those of you who don't want to listen to the explanation I am now going to give, can close their ears, because I am going to quickly sketch the proof. I mean, tell you the idea. When you want to solve the exercise, here's the idea. You convert it into a precise argument. And so for those of you who don't want to look at it, don't look at it. Now, so suppose this has a disconnection. So disconnection will be two sets. Let's have one blue set, something like this. The blue set goes like this, and the other is the yellow set. Maybe there again some blue showing again here. Maybe there's yellow showing again here, and maybe there's a yellow part here and another yellow part here, etc., etc. So suppose the blue set is U. Okay, U is the blue set, and the yellow set is V. And now I'm going to assume that U not equal to empty, V not equal to empty, U intersection V equal to empty, and U union V is equal to 0, 1. So we can assume, without loss of generality, that 0 belongs to the blue set. Now, 0 is not the only point. There are other points, and blue set is not the only set. Of course, if 0 belongs to the yellow set, you interchange blue and yellow for the sake of this argument. So now take some point. So this is 0. Take some point in the yellow set. Okay, that point may be B. Okay, take that point B. Take that point 0, B. So this is the interval AB, which I want to show is connected. I'll show this part is connected. You know, this interval is homeomorphic to the original interval, of course. So it doesn't matter what interval I show is connected. So I'll focus attention here. So there are various points in the blue set and various points in the blue set, but I want the first yellow point, so to say. So look at the set of all blue points such that any point smaller than them is still blue. And that set will have supremum. Okay. And now the question arises whether that supremum point of that continuous blue part is blue or yellow. If it is blue, because blue is an open set, there will be a whole interval around it which is blue, which means there will be some further points which are also blue. So then that point can't be supremum. That point cannot be B, because B is a yellow point. So there are necessarily some further points. Otherwise, you will say, well, this may be the maximum, so there is nothing further possible. But no, this point is not B, this supremum, because I have said U is open. So the supremum point, if it is in U, I have a problem. So the supremum point is in V. Yeah, that may well be the point B. but then V is also an open set, so all around it are yellow points. So even before it are some yellow points, and then they cannot be blue points. Blue and yellow is intersection is empty. Then how could this point have been supremum of blue points? Contradiction. So this supremum point can neither be blue nor be yellow, contradicting this, that their union is everything. Yeah, so I have told you the proof by drawing pictures. So for those of you who heard this pictorial proof, exercise is you write down a rigorous proof. And I don't know whether your tutors take submissions from you. Time to time I see WhatsApp messages of your group, and where the tutors are saying, hey, blah, 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 submit exercises. And which perhaps means that you guys write and submit exercises. Very good. In that case, you can try writing this and submitting. This is very, very elementary basic exercise. This is also a favorite question in BSc or MSc or whatever examinations. So make sure you know this proof very well. Okay. So any questions on this, that the interval is connected or real n is connected? I hope you understood that. Now I'm going, instead of, I asked you one more question here, but we'll return to it later. So this question we will address later. Okay, important question, and this will address later. Instead, now I want to introduce another notion, and that's called path connectedness. Let me type this. The idea behind path connectedness is very nice. The idea is that, suppose I have this interval, okay, which I use as time interval of 1 hour. And here is a place. That place is another topological space X. And there, well, place, I may call it a town or whatever. In that, there are two locations. One let us call X0, and the other let's call X1. And you want to travel from X0 to X1 in a continuous manner. So this is I, which means you need a continuous map F from the interval, time interval into the space, and which takes this interval, and let me give it some red colored. So time is colored red, okay? And that means as time passes, you trace a certain path there, and you start from X0 and end at X1. This is the path traced by this F. T goes to the point Ft. Any point T goes to Ft. This X is F0, X0, and this X1 is F1, which means you begin at time 0, you begin at X0, then as time passes, you continuously move around, and at time 1, when the hour is up, you are arrived at the other point, okay? So if there exists, so we say if given any X0, X1 belonging to X, there exists continuous F from 0, 1 to X such that F of X0, sorry, what was that? So that F of 0 is equal to X0 and F of 1 is equal to X1. Then we say that X0 and X1 can be connected by a path. This is a parameterized path. And if this happens for all x0, x1 in X, we say that X is path connected. Okay, so this any I should remove from here. And here I'll say let. And here suppose there exists a continuous function, so then we say this is why. Okay. So I am now going to show you a space and you tell me whether it's path connected. The space is a subspace of R2 and it looks like this. It has two parts. Can you go with a continuous path from x0 to x1? Can you? No. In general, if a space is disconnected, there's a space, there's U and there is V. And if there's a map from I into here, okay, and x0 is in U and V, then you will have F inverse U is not empty, okay, because 0 lies there, 1 lies in F inverse V, okay, and F inverse U intersection F inverse V equal to empty, and F inverse U union F inverse V equal to F inverse of U union V equal to I. This would be a contradiction. As 0, 1 is connected. So we have therefore proved the statement that, therefore we have proved the proposition if X is path connected, then X is connected. The converse is false. Okay. There are connected spaces which are not path connected. And I'm asking you, give example. So you have understood the notion of connected and path connected, and its opposite disconnected or something which is not path connected, and the implication that path connected implies connected. The other general notion of connectedness I like to introduce is that of connected components. So on this I'll go slowly because a lot of misconceptions are possible on connected components. Yet another notion I like to introduce is that of a locally connected space. Another one I like to introduce is locally path connected space. And yet another notion I like to introduce is that of path components. These are kind of different things that I like to introduce. So if I begin now, there are only 5 minutes left. So I am at a loss of whether I should begin on this and then repeat all over again and therefore spend almost the same time, or start on all this tomorrow. So I'll rather start on all this tomorrow, and instead let me go back to Hausdorffness and show you one little property. So here's the last new statement I'm making, and after that we'll revise. Okay. Exercise. Let G be a topological group. Let H and G be a normal subgroup. And G to G mod H, the group quotient. Okay, give G mod H the quotient topology. As we described, whenever I have set and a cancellation, the quotient gets a topology. Namely, all those sets are declared to be open whose inverse image is open. Show that G mod H is Hausdorff if and only if H is closed in G. Exercise clear? Somebody's. And now again, remember, Hausdorff should not send you into take one point, take another point, try to make disjoint neighborhoods and choose some neighborhood, blah, 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 blah. No need at all. The exercise should come straight from the diagram. Therefore, let's see. Okay. If I take, yeah, so if I have the diagonal of G mod H, and inside this, take the diagonal. And to this, take some map, okay, and somehow leverage this information into inverse image of this being H. So can you make this? I have given you a hint that you have to think of the closed subset, namely diagonal of G mod H, and somehow leverage it into the thing that we want. Or you can think of G to G mod H, and G mod H is Hausdorff, and therefore this is closed, and its inverse image is H. This is closed. Inverse image of something closed is closed. Okay. So even simpler. You don't even have to think of diagonal if you are willing to use our earlier exercises. Very good. So simply go back to our earlier exercises which said, when is a group Hausdorff? A group is Hausdorff is equivalent to identity being closed. So G mod H is Hausdorff, which means the identity E there. The identity E there is the coset EH, in other words. Okay. So the inverse image of E is just H. That subset. This is closed, means this is closed. Conversely, because this has quotient topology, any set whose inverse image is closed is declared to be closed. So if H is closed, then E is closed, and then G mod H is Hausdorff by all those equivalences which are viewed using the diagonal. So we are given a proof without saying take 2 points and manufacture 2 disjoint open sets. Yeah, so this is the exercise. I have run out of time now, and it is therefore I'll not say anything new, and you can ask any questions. I'll do a countdown from 10 to 0, and so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So there are no questions, and so I am ending this lecture. I'll begin by stopping sharing this